Ladies and gentlemen, welcome, and thank you for joining today's conference, the Annex 4 Environmental Research Webinar Series. Please note that all lines will be muted for the duration of the call. You are welcome to submit written questions during the presentation, and these will be addressed during Q&A. To send a note, select Participants at the top of your screen and opt to send note to all presenters. If you have logged in using the web-based application, use the Notes tab on the bottom right-hand side of the screen and address your note to all moderators. If at any time you require technical assistance, you can call the help desk at 888-796-6118 or simply send a note to the ATT CES operator via the software. With that, I'll turn the call over to Andrea Copping, Senior Program Manager for Coastal and Marine Waters at Pacific Northwest National Laboratory. Please go ahead, Andrea.
Thank you. And welcome to everyone joining us this morning or this afternoon for this Annex 4 webinar. Many of you may know that Annex 4 is an international collaboration under the Ocean Energy Systems Agreement that looks at environmental effects of marine renewable energy. We're very pleased today to have two speakers on the topic of artificial reefing and benthic effects of marine renewable energy devices. Our presenters, Sharon Kramer and Olivia Longhammer, will be talking on these two topics. Next slide. We'll start with Sharon Kramer. Dr. Kramer is a principal at H.T. Harvey & Associates, and she heads the North Coast office and the fish ecology team. She has more than 30 years of experience in aquatic ecology and fish biology. She's worked in the Pacific Northwest, California, Australia, and Hawaii. Sharon's well-versed in fish and aquatic habitat restoration and monitoring, as well as project permitting and extensive federal Endangered Species Act work. Her most recent focus has been involved permitting, assessing, and mitigating the environmental effects associated with marine renewable energy projects. So Sharon, would you go ahead, please?
Thank you, Andrea. Again, here's our title slide. I want to just mention that thank you for joining and good day from the U.S. West Coast. I will discuss this qualitative study that was funded by U.S. Department of Energy and the Bureau of Ocean Energy Management. We conducted this study to really evaluate the potential for marine and hydrokinetic projects or devices. This does apply, however, to offshore wind as well, to act either as an artificial reef or as artificial reefs or fish aggregating devices. Next slide, please. I want to give you a little bit of background on the work and on myself from the perspective. I have worked in the past as the National Marine Fisheries Service researcher as a regulator with National Marine Fisheries Service and U.S. Fish and Wildlife Service with the advent of the Endangered Species Act listing of numerous fish species, and then became quite involved in the permitting and licensing process for the Federal Energy Regulatory Commission, primarily with hydroelectric power. And then when the marine renewable energy and MHK industry began to really appear in the U.S., I switched back into this sector. And so my perspective really is almost a 360-degree perspective on the permitting licensing process for these projects, understanding sort of the research questions as well as the regulatory permitting needs, and also this sort of industry side. So I try to look at it in a 360-degree approach. So my perspective and the reasoning for this project really came from experience I had trying to permit and license 3 projects, I'm looking back now, on the West Coast, and they're highlighted on this graphic. So the first project to the north, well, let's actually start at Reedsport. There's a graphic with Reedsport, Oregon, highlighted, and that was Ocean Power Technologies' wave energy project, which was licensed and surrendered, followed by then the Snohomish Admiralty Inlet Tidal project to the north in Puget Sound, and that was also completed but surrendered. And then to the south in the very northern part of California, the Humboldt Wave Connect project, which was not completed. However, the licensing was well initiated. And I noted in all those projects that there was this question, the same question, which was, what is the effect of having this hard structure in the water? And in all three cases, we were designing studies to address that question. And those studies, if you work in the marine environment, which most of you do, are not easy or cheap to do. They're very, they can be very challenging and very expensive. So it made me want to start to explore how we could address this question, at least for the purposes of permitting and licensing, with respect to what we could learn from surrogates, one, and two, research conducted for other reasons. The geographic scope of this project was Hawaii and the west coast of the U.S. Next slide, please. So this is a graphic from a project I'm currently involved in. I would say that this project, which is the Northwest National Marine Renewable Energy Center from Pacific Marine Energy Center South Energy Test Site at Oregon State University off Newport. I like to show this graphic because it sort of gives you this realm of the potential environmental effects. And so, again, this study is focusing really on the sort of structure, attraction of rock-associated species, hard structure, and fish assemblages, as opposed to all the other potential environmental effects. And one of the things that obviously we're trying to do in the U.S. and other places is a focus on efforts to try to retire or understand these risks so permitting can be conducted and monitoring can be focused on these more misunderstood or uncertain effects once devices are installed. Next slide, please. So what do we mean by artificial reef and fish aggregating device? So I wanted to just at least give you a little background on how we focused on these effects. Fish aggregating device, generally what we considered was sort of these temporary associations of fish with structure in the water, primarily in the midwater and surface structure. And I'll elaborate a little bit more on that later, but the MHK, or Marine Renewable Energy Device, equivalents would be the mooring lines, the devices themselves, and any buoys that would be used for marking or aids to navigation. And what do we mean by artificial reef? In this case, we mean really the hard structure that's used to anchor devices to the seafloor. And here we mean really resident fishes that are more attracted and required or have a requirement to use these high relief habitats. In both cases, we usually get invertebrate colonization or attachment to these surfaces, so the structures do change over time. Next slide, please. So what kinds of surrogates were we able to evaluate? We looked at natural features such as natural reefs and kelp, be it attached or floating in kelp patties. We looked at artificial structures, including FADs, fish aggregating devices, which are purpose-built for the purpose of providing fishing opportunities, both commercial and recreational, as well as for research. We evaluated mariculture net pens, oil platforms, marine debris, and artificial reefs. So I will show you as we go forward that not all these structure types occur in all locations. So it makes it a little difficult to compare across regions, but we did our best to do that. So let's go to the next slide. So what did we learn from surrogates? So what we learned, oops, can you go to the next slide, please? Thank you. What we learned was information on, obviously, the fish assemblages. So we were interested in knowing the primary species most likely to use the structure, but also the question came up, and it is a big issue in the U.S., whether special status fish species interactions are occurring. And this is important because these are fish that are considered more highly or scrutinized more highly because they're either listed under the Federal Endangered Species Act or different state acts. So they become a higher consideration for permitting or licensing. We also were interested in how these ecological interactions may change over time. So do these projects mature? And then looking at interannual and seasonal timescales where we could do different types of oceanographic variability, such as an El Nino event, change the fish assemblages. Next slide, please. So our approach was very straightforward. We first decided to analyze 4 regions. We looked at 3 off the West Coast and 1 in Hawaii, and Hawaii is a region. The 3 West Coast regions included the Southern California Bight, which is south of Point Conception roughly and south, from Point Conception up to along the Washington coast as another region, which I'll refer to probably as cold temperate, and then Puget Sound. So those were the 3 West Coast regions, and then Hawaii. We conducted a literature review of what we could find on the surrogates in all these regions, and then we probably very valuable was we held guided discussions with subject matter experts. And these were people that had generally direct experience with the surrogates for other purposes. So their research or their findings were not to answer our question, but they had questions that they were addressing or issues that they were studying with these other surrogates. So in general, the subject matter experts had, for example, a large, high number of ROV, remote operated vehicle surveys, associated with their studies, and these could include, again, natural reefs, marine protected areas, marine debris, diver observations, for example. So we asked them to describe their work, and then we asked them questions about how their work might help address the questions we were trying to answer about offshore marine renewable projects. And we tried to account for several variables, including the deployment depth, the time in the water, the type of invertebrate colonization, and again, the fish types that were present and their life stages and the commonalities. In other words, how likely were those fish species to occur. And again, we also kind of qualified how certain their observations were, if they were very certain versus less certain. So again, this is a qualitative project. Can we go to the next slide, please? Great. So now I'll walk you through the sort of a little bit about each region and some of our initial findings. You really need to go to the report, and there's a link at the end of the talk to get to the report, because there's a lot of detail in the report. So the first region I'll discuss is the Southern California Bight, which actually had the greatest number of surrogates of all the regions. And so you can get a sense on the right-hand side of the types of surrogates and their numbers. So again, we had natural reefs, artificial reefs, and in Southern California Bight, we had oil platforms. We had some mariculture net pens just south of the U.S. border in northern Baja. We had what we call purpose-built fads. I'll talk about that a little bit. Kelp and marine debris. So these were studies that were evaluated on those surrogates. Next slide, please. These tables are massive in our report, so I try to give you just sort of a quick snapshot of what they look like. So again, we looked at the fish associations, the fish families, for example, that tend to be most associated in Southern California with especially bottom structure, were the scorpenids. So these are Boccaccio, the rockfishes, the cowcod, et cetera. They tend to be very highly associated with structure on the bottom. So again, what we have is position of where the fish were observed in the water column. Were they affected by the depth that the bottom structure was in? And we kind of binned those depths very deep, out like even to 1,000 meters, and then shallow. And then were they associated with the midwater structure or surface structure? So were the fish attracted to, if you will, the structure as a fad? And so we went through all the different species and assemblages and what we could find and summarized these in gigantic tables in our report. I'll note that a couple things that besides the fish families, the scorpenids, which are commercially and recreationally important. Down the list is the steelhead, which is a listed species. It's found, very rare, but found in Southern California, primarily in spawning in streams and rivers down there. And then the bluefin tuna, another managed species, again, of interest. So we tried to incorporate what we could find on all the species of concern for management purposes, not just all species and the management-related species. Can we go to the next slide, please? Thank you. So this next region is a very long region that really starts at Southern California Bight, Point Conception, and goes all the way up to the coast of Washington. And you'll see that there are much fewer surrogates. And there's a lot of reasons for that. One being that there isn't oil and gas really past that Point Conception very far. So you don't have the oil and gas platforms. And the states to the north, and even California to some extent, is not really promoting artificial reefs. So we don't have a lot of artificial reef structure to learn from. So again, this region really was limited as far as the number of surrogates. And there are some uncertainties because of that. And now here, when we say purpose-built FADs, off the central coast of California and up north, these fish aggregating devices were not used for recreational or commercial fishing. And in fact, we were unable to find any solid reference to people intentionally fishing off any devices, including offshore aids to navigation, for the purpose of catching a lot of these fish species. So what there has been is deployed the standard monitoring units for the recruitment of temperate reef fishes, or SMRFs. Those are what I lumped into purpose-built FADs, and they are research units used to look at juvenile rockfishes. So I'll elaborate a little bit more on that later. So most of the research we were able to gain was from looking at marine debris off the coast, and also just ROV footage that was taken for the purpose of really understanding marine protected area baseline. Next slide, please. Again, just a snapshot. That's why you see et cetera. We didn't want to have these long tables for the presentation. Same format. But again, what we focused on here were a couple of species that are listed under the Endangered Species Act, in particular green sturgeon and eulachon, which are species again, they're listed under the Endangered Species Act. They are a priority to understand their effects because of that for the licensing process. So as an example, green sturgeon would primarily be a benthic or bottom-oriented fish, although they do swim vertically as well. And would they be affected by the depth of the bottom structure? Yes, because they don't go that far offshore. And are they associated with the midwater structure or the surface structure? Probably not. But there is some uncertainty again. But again, this is just a summary of what information we were able to put together. Let's go to the next slide, please. Puget Sound. Thank you. Again, there were fewer structures that we were able to glean from. In Puget Sound, though, it's not wave energy devices that are of interest. It's tidal energy devices. I'll say that first. Again, there are some natural reefs and artificial reefs in the Puget Sound area, kelp, drifting kelp, floating debris, and very little information on mariculture net pens to the north in British Columbia. There is more information, but there just isn't a lot published about interactions with mariculture net pens. So again, the types of surrogates and their distribution is very different by region. Can we go to the next slide? Great. And again, same sort of summary. Again, this one focuses on the species that are listed under the Endangered Species Act and whether the fish are more associated with, and their life stage, associated more with the water column or the benthic part of the structure. And then let's move to the next slide. Now, Hawaii, as you know, is very different. It's tropical. And here, wave devices and offshore wind are being considered, wind particularly, offshore wind. And here, we had studies of, there are mariculture net pens that we were able to get great information about, and the fish assemblages associated with them, and marine mammals actually is very interesting. But here, in tropical waters is where you actually see fish aggregating devices, or FADs, deployed by the state of Hawaii, in fact, to promote commercial and recreational fishing opportunities. So this is a place where, and fishermen can tell you a lot, where FADs do work to associate fish. So let's move to the next slide. This slide focuses on the bottom fish association. These are the Lucianid or snapper fishery, which is a really great interest in the state of Hawaii, and reef associated. So you can see structure in the water definitely does attract the bottom-oriented snapper fish, which are managed by National Marine Fisheries Service in the state of Hawaii. I didn't elaborate here on the FAD effect, but again, in Hawaii, purpose-built FADs are built and deployed to attract tuna and other pelagic fish. These fish generally are associated with the structure for days to months, and there's been a lot of study on FADs and how fish are associated and how long, because it's a fishery that's promoted, and the distance offshore affects that assemblage. So closer to shore, you get a slightly different assemblage than you would further offshore. So we have really good information on FADs, which are numerous in Hawaii. Can we go to the next slide, please? Thank you. So we compared also how the surrogates might actually relate to the structure of a wave energy device or a tidal energy device, and their distribution and number in each region. So to give you again an idea of the problem with looking at surrogates and the availability of surrogates across regions. So for example, there are net pens. If you look at the net pen mariculture net cage, there's a lot of similarities between those structures. They've got moorings, they've got anchors, they've got surface relief, surface structure, but there are very few of them available for us to study. So they're a great surrogate, but we just don't have a lot of them available to us. And we learned a lot from talking to the people that do use net cages for raising fish. Same with purpose-built FADs. Again, they're all over in Hawaii because they work. They do associate fish. That's a very well-known phenomenon. We don't have very many purpose-built FADs other than for research purposes, really, off the West Coast. So what we can learn is very different. So again, this is just for the purpose of sort of looking at our surrogates and weighing out whether we're comparing apples and oranges or not. Next slide, please. So again, very qualitative summary of our findings. Our findings suggest that the FAD effect is very certain. So on the left, you'll see a certainty bar, and the right, an attraction bar or association bar. The FAD effect in Hawaii is highly certain, and there's high attraction, and it's very well known. But as you move to the West Coast, the certainty for the FAD effect starts to decrease. In Southern California Bight, there have been numerous studies of floating kelp and other types of structure, but the fish associations are very certain life stages of certain species of fish, and very, very short term. So we were unable to really say with very much certainty that Southern California Bight really does have a structure would act as a FAD. However, certain year types, it did matter. So I'll touch on that too. El Nino, when you get tropical waters or warmer waters coming up from the south, you do get an assemblage of fish that moves to the north, and these do become prevalent in the Southern California Bight, and those are the times when you might expect a FAD effect to occur. So it's not all the time, primarily during certain oceanographic conditions. And then off Central California and all the way up to Washington coast, it's less certainty because we had very few FADs to really evaluate, but also if you understand how FADs work and the theories or hypotheses about why they attract fish, they are primarily a clear water tropical phenomenon where fish become attracted to the structure for a while and then move on. Again, these are pelagic fish, highly migratory, move great distances. Typically, those types of fish are not prevalent off the cold temperate coast. So our thinking is that there probably is less of an attraction, but we have also less certainty because we have less structure to really understand this. Whereas in the artificial reef column, if you notice, all regions, any structure, fish are attracted and use the structure. So again, these are reef-oriented fish, resident fish that tend to need structure or relief on the bottom, and they will use any relief, be it from sand relief or sandstone, small, tiny, tiny features. They will use those features all the way up to, again, larger reef structure, highly complex structure, and the structure does make a difference, the complexity of the structure. So we were able to at least ascertain, as people know, artificial reefs do work, but we were not able to say that it was a positive or negative effect. In other words, was it a source or sink? That was not what our purpose was. It was more to understand what assemblages do form. Next slide. Thank you. Again, the uncertainties. There is some uncertainty about the FAD effect in temperate waters and cold temperate waters. We know for sure juvenile rockfish will associate with surface and midwater structure, and then as they grow, they move down to the benthos and then they will then inhabit reef-type structure. So that's well understood, but if there are other types of fish that are attracted or associated with this surface and midwater structure, it's a little less well understood. However, this could be evaluated pretty reasonably without putting any device in the water by looking at Coast Guard aids to navigation. There already are structures off the West Coast that could be evaluated. In interviews with Coast Guard personnel, we were unable to ascertain any observations from them, but they're not ecologists. They're doing maintenance on these aids to navigation. So again, less information, but certainly we do have structure out there that could be studied. Our sampling and our evaluation did not allow us to evaluate the scale of installation, the effects of the scale. Generally, the surrogates were not in arrays or multiples where we could talk to people about artificial reefs or reef effects. We did try to ask them about potential for small, numerous reefs versus complex reefs, large reefs, and we did get some information, but we don't really have effects to sort of understanding of effects to push it out to the installation scale. And we do feel that adverse effects on special status species are unlikely, but again, they're rarer species. And there are studies that are ongoing using telemetry and other types of evaluation methods that may elucidate that. And so next slide, please. So we're hoping that the study helps to inform permitting. In particular, we had a lot of uncertainties that can hold up permitting, and so this supports the analysis of environmental effects for NEPA and Endangered Species Act documents. But the focus really, we were really hoping to focus where we need to monitor and where we need to improve our understanding so that we can not have to do extensive monitoring at every project, at every site. That was another goal. Next slide, please. I want to acknowledge, I won't read the list, but we had some really incredible people that agreed to talk with us, and these included resource managers, academics, and mariculture industry participants. So we were really fortunate and having a really great group of people to work. And final slide, just for more information, my contact and where the reports are available, including on the TEFAS site. So at that, I will end. Thank you.
Sharon, thank you very much. Great succinct presentation of a large but really useful report. So I would encourage everyone to go to that site and check out the report. Okay, our second speaker today is Olivia Langhammer. Dr. Langhammer grew up in southern Germany but did most of her graduate work in Sweden. at Uppsala University, where she looked at environmental effects of wave power devices. She then moved to a postdoc at the Norwegian Institute of Science and Technology, where she looked at populations of fish and crabs and their response to offshore wind. She's recently joined the Department of Energy and Environment at Chalmers University of Technology as a research fellow, and she'll be working on investigating and mitigating environmental impacts of hydrokinetic turbines. So she's really got a good grasp of these kinds of issues across the sets of technology. So please, Olivia, go ahead.
Thank you very much. Thank you, Andrea, and thank you, Sharon, for your very interesting presentation. Together with my colleagues, we've been working on reef effects of offshore wind and wave power parks, mostly in Sweden. And on the next slide, you see a bit more about my research interests. So I'm mostly interested in marine renewable energy conversion and the marine environment. Between 2005 and 2009, I've been at Uppsala University as a PhD student at the Department of Animal Ecology, working together with the Ångström department on wave energy conversion and the marine environment. And then later on, I went to Trondheim, to NTNU, and there I was at the Department of Biology at the Center for Biodiversity Dynamics, and looked at population dynamics in an offshore wind park. And here you can see, there are two different devices I was focusing at. On the upper side, you see a wave power foundation, and on the lower side, you see the offshore wind park in Lillgrund. And I will talk a bit more about it soon. On the next slide, you see why it is important also for marine renewable energy installations to focus on sustainability. So if you include early environmental challenges in marine renewable energy projects, such as the effect that in general there's a loss of biodiversity and ecosystem services reported by IUCN. And for this reason, good science is needed to have an impact on stakeholders and society to allow a smooth transition towards sustainability. So you have different anthropogenic changes, and that can be really seriously. And here on the right-hand side, you see the Great Barrier Reef. I guess it's a fantastic place. I've never been there, but as you can see, really high biodiversity and growing coral reefs. But during the last years, there have been like a loss of the corals. About 2/3 of the shallow corals were lost during last years during global warming. So sustainability is a really important issue, even within offshore renewable energy. And on the next slide, you see our focus. It's artificial reefs that are submerged structures deliberately placed on a seabed to mimic some functions of a natural reef, such as protecting, regenerating, concentrating, or enhancing populations of living marine resources. So you can see the reef balls on the left-hand side, and they are by far the most used designed artificial reefs in the world. They used to create habitats for fish and other marine and freshwater species, and are used in about 62 different countries. And on the right-hand side, you see Runde Reef from Reef System, and it's out of PE plastic pipes. These are 16 vertical rows of 2.5 meter plastic pipes, and they have been studied in Norway. They've been deployed along the Norwegian coast, mostly in the north, and they could show some aggregation on colonization of fish and algae, kelp, worms, etc. And I will talk about these two reefs later on, so you can keep it in mind. And on the next slide, you see different reasons for deploying artificial reefs. And you can, some are trying to enhance the fisheries, and it also shows that a FAD effect, fish aggregation device, in order to enhance the fisheries. So you can create new habitats in areas, for example, these that are dominated by soft bottoms, and mostly they are deployed for preservation and rehabilitation of marine habitats, as in the definition I said before. Many artificial submerged structures do not have the primary function of reefs, but will inevitably be colonized by organisms. And on the next slide, you see some factors that may influence the colonization process of artificial reefs. For example, the location or the height and how complex the reef is. And that really matters when you try to build or design reefs. And and how well artificial reefs mimic natural habitats, especially in their role in maintaining ecosystem services and marine biodiversity, is a cause for concern. And of course, it needs discussion, and especially in a world of increasing urbanization. And artificial reefs may host communities that are different to those of natural reefs. They can also host invasive species and also modify the diversity of species in nearby habitats and areas. And when a hard substrate is added to form a soft bottom, it can significantly change due to new trophic opportunities, and also due to changes in local food webs. And on the next slide, you will see again the two different sites where me and my colleagues have been studying and working at. One is the Lillegrund offshore wind farm, which is between Copenhagen and Malmö in the Öresund Strait. And then, this is a wind farm that consists of about 48 turbines, and it's been established in 2007. And I will tell you a bit more about it later. And in Lysekil, there's a wave power research site. It's about 100 kilometers north of Gothenburg. And I was getting involved during my PhD. And now I'm still involved by co-supervising PhD student Anke, who's also as participant in this webinar. And in general, we've been looking at artificial reefs. We conducted studies on motile organisms and epibenthic sessile organisms in the Lysekil research site. We've been looking at biofouling and also on the surrounding sediments and soft bottom studies have been conducted. But now I will just talk about the reef studies. And on the next slide, you see our research questions. And and mostly the focus was, what are the effects of wave power foundations on benthic species distribution patterns of mobile organisms in this area? And to what extent will the deployment of wave power foundations on barely sand bottom affect local distribution patterns of motile species? And also, what are the effects of low-cost enhancements of shelter availability and compartment through holes? You can see it on the pictures there. We have done some small holes. We've designed some small holes in the wave power foundations, which you see on the left side, in order to increase the complexity. The foundation on the right is only concrete block, more or less, round, and both weighed about 10 tons. And behind the left picture, you see the wave power buoys. We have been looking on a biofouling effect too. And and here we wanted to know what's happening on and around the foundations directly after deployment and 1 year after the deployment. So we also have been looking at control sites that were 10 meters away from each foundation, and we were inspecting the holes in and the cavities underneath the foundations for all organisms that were aggregating. On the next slide, you can see the experimental setup. First, there's a short, a small overview. And there you can see the focus of me was on the biological buoys and the foundations, which is yellow. And then you see other constructions and devices that have been out there in the place or still out there, like the generators. They are linear generators absorbing the waves and going up and down with the wave movement. And we have a measuring station out there, a marine substation, a wave measuring buoy, and an observation tower too. And the other picture shows the experimental setup in the area. So you have some green squares and one green star, and these are foundations that have been placed late 2005. And then we also have this red squares with the flags on. And these are foundations that were placed out during early 2007. So in total, there were 26 foundations during my studies out there, and 14 with holes. So you can go to the next slide, please. And here you see the mean abundance of benthic species recorded on wave hole foundations in 2007. In general, there were no invasive species that have been observed in this area and on the foundations. And here you can see the taxa, the foundations without holes, the foundations with holes, total abundance on the foundations compared to controls. And for example, the edible crab underneath the decapods, you see it's a typical reef aggregated species that we have been observed in this area. And the presence of artificial reefs did not seem to influence numbers of, for example, common starfish, hermit crabs, and spider crab. 8 species of fish were recorded on the foundations, while 3 species were noted in the controls. And if you go to the next slide, you can see the fish abundance and number of species observed in the Lucifer wave hole site. So on the graph to the left, you can see that fish abundance was generally low, but significantly higher on the foundations than in the controls. There were only a few fish that used the designed holes, and no effect of holes on fish abundance was shown. No fish was found in the upper holes. We had upper and lower holes. And in the bottom holes, they were occupied by 3 fish species, by the rock gunnel, by the bull road, and by the Atlantic cod. On the right-hand side, you see 2 graphs. The purple blocks are the foundations, and the pink are the control areas. And it's not significant, but it's a trend towards a higher number of fish species and a higher fish abundance on and around the foundations we found. And on the next slide, you see the reef aggregated colonization patterns of edible crab, and the abundance of Canthropagurus was positively affected by the foundations and also by the manufactured holes in the foundations, what you can see in the graphs. The edible crab uses the upper holes located 0.5 meters above the bottom more frequently than it used the holes along the bottom. You can see it on the right-hand side. And then we also found some lobsters. They were digging their themselves into cavities underneath the foundations. So we had one European lobster and one Norwegian lobster using the foundations as shelter. And on the next slide, you see another study that was more or less like a paper study on the potential for wave energy devices to provide artificial habitat and protected areas from fishing. And so we did a literature review together with my colleague, Dan Wilhelmsson, from a scientific database. And further on, we looked at case studies on the potential of these wave energy devices, with a focus on two different regions. One was in Ireland, at the coast of Ireland, and another region was Norway. And then we were looking at three different technologies: at sea-based, Pilamis, and wavebob. And yeah, here we concluded, or you can see zero, that means no effect. The plus, 1 plus means likely to add biomass, but in limited numbers. 2 pluses, likely to add biomass in moderate numbers, and 3 pluses is likely to add biomass in considerable numbers. And here, our conclusions are that the responses to the different types are species-specific, and available data only allow for qualitative estimates based on scientifically founded speculations. And yeah, here in the table, it looked like the sea-based device will influence distribution patterns of fish to any noteworthy degree. In shallow waters above 50 meters, it's possible that sea-based generators and foundations affect pelagic fish in a positive way, so attract them. And in another study, you can see it on the next slide, thank you. They did a review on artificial reef effect in relation to offshore renewable energy. And here you can see the reef effect when it comes to scouring protections. When constructing, for example, these protections, since it can generate and enhance habitat, it creates increased heterogeneity, and that is important for biodiversity and the species density. And the scour around, for example, wind power or the erosion is the removal of seabed material around coastal structures by hydrodynamic forces. And this can result in up to 10-meter deep sediment reduction around the turbines. And usually, you are using gravel protections and boulder protections and synthetic fronts. They are also discussed. And the gravel and boulder protections, they're used in one or more layers and are aggregated around the turbine base, shaping a circular reef of 10 to 50 meters in radius. And hard substrate generally has a higher biodiversity and species abundance than the surrounding soft bottoms. But in comparison to boulders, the gravel protection will result in lower diversity because it's a more unstable environment there. When you look at the synthetic fronts, they are polypropylene fronts that resemble seaweed beds, and they accumulate soft sediments over time and build up a cohesive underwater sea bank. So there's no really increase in biodiversity, for example, and there's no reef effect. And then there were this alternative designs. They can function both as scour protections and as artificial reefs, and seem to be really effective, both the reef ball and the sea coat. And they are really positive for, they increase the biodiversity, but it has a high cost, of course, due to specific reef design. So, and now you can go on to the next slide, please. And here you see the species aggregation around offshore wind turbines. with the Scour protections and without Scour protections, and also around gravity-based foundations. There have been some studies conducted. And for example, poaching and cod has been studied and it looks like they are aggregating around the monopiles. And the same with the pelagic and benthic species assemblages on monopiles without Scour protections. In gravity-based foundations, there has been shown that several kinds of species, reef aggregated species, have been found around these foundations. And it was a study from Lillegrund, where we also have been. And in general, there are several fishing surveys and monitoring programs that have been conducted at offshore wind farms. They were targeting large mobile pelagic fish over large spatial and temporal scales with telemetry tagging, for example. But most of the surveys, they have not been designed to capture the artificial reef effects, at least in terms of survey design and methodology. Still, some surveys and studies could show an aggregation or attraction of motile fauna around wind farm turbines. And in the picture you see the Lillegrund offshore wind farm, which is between Copenhagen and Malmö. And there you can see it on the next slide. We've been conducting studies there on populations of the shore crab, or you call it green crab in the US, and the viviparous eelpoot, that is a sentinel species and used as bioindicator in the Baltic Sea. And there we have been conducting marker capture studies using fyke nets. And so we were tagging the eelpoot and the crabs with T-bar anchors in the offshore wind farm and in 2 control areas in order to estimate population size and population density. And the crabs, we've been looking on morphological traits and sex ratio and condition as well. And the eelpoot, we've been studying the condition index, histosomatic index, should be HSI, and gonadosomatic index. And also we've been conducting some brood analysis of pregnant eelpoot too. And here we wanted to test the hypothesis that crabs and eelpoot will be more abundant in the Lillegrund offshore wind farm compared to a adjacent control site due to added new habitat. And I expected also difference in morphological traits between the offshore wind farm and the control site. We can go on to the next slide, please. And here you see the results when we've been looking at the shore crab, Carcinus menas. And on the left side, you see the catch per unit effort in 2011 and 2012. And this is in Lillegrund, which is the offshore wind farm, and Skjolden and Bredgrund are the 2 control sites. And the catch per unit effort showed a significant interaction between the site and year. Catch per unit effort was significantly higher in 2011 compared to 2012. And Lillegrund and Skjolden control site had a higher catch per unit effort than Bredgrund. And when we've been looking at the mean size of the carapax of the shore crabs, it varied in all populations, with the widest mean size in Bredgrund, control site, and the smallest in Skjolden, also control site. So Lillegrund was in between. And it was a yearly variation in Lillegrund and Bredgrund. And we observed very low recapture rates. In total, we captured 5,957 crabs and marked them, but it was about 1% of recapture rate. So it was really tricky to do some population estimates. But the conclusion of the study was that there's no clear artificial reef effect in Lillegrund, but a spillover effect to nearby habitat. It cannot be excluded. And on the next slide, you see the study on the viviparous eelpout, Surrogates viviparus. And here you see the graphs of the weight of the fish, the gonadosomatic index, histosomatic index, and condition index. And the female eel pod caught in Lillegrund offshore wind farm, which is number 1 in all the graphs. 2 is the control. It was generally heavier than in the control site, but not longer. The length-weight relationship is expressed by the CI, condition index, and varied considerably. It was highest in 2011 in both sites. The HSI, histosomatic index, had an interaction effect, and the gonadosomatic index was significantly higher in Lillegrund and differed significantly between the years. And the marking experiments with the population size estimates in Lillegrund lied between the 2 control sites, and neither an aggregation or an avoidance of the area has been the case. So in conclusion, there's no clear artificial reef effect there too. Attracting the eel pod to the foundations and scour protections of the offshore wind.
And Andrea, if you'd like to go ahead and we can start our Q&A. I'm going to go ahead and reopen Olivia's line. She had gotten muted. So Olivia, are you back with us?
Yes, I'm back again. I have
Olivia,
2 more sentences.
Yes.
So,
are you done?
Yeah, this
Olivia, go ahead.
This can be explained by already existing hard substrate in the surrounding of Lillegrund, or due to increased predation pressure from other reef aggregated species occurring in this area and controlling eel pod densities. So still there, you know more, but still there are a lot of question marks. So we need, of course, more studies, more research, and we are also working on it. So thank you for me.
Thank you, Olivia. That was really, really in-depth and insightful. Appreciate, and it's clear that there have been a lot of studies done in this area, particularly in Europe, and I think that's something we can very much learn from in other parts of the world. I want to go to the next slide, please. Okay, we are going to pose some questions that have come in on our online system for the speakers, and I would like to encourage the audience, if you have other questions, to go ahead and type them in the dialog box. So the first question here is actually directed at Sharon Kramer. The question is, did the study of surrogates include any secondary attraction of fish predators to the devices, for example, seabirds or others?
Yeah, the short answer to that is not really. We did ask the question, though, did we see larger aggregations of pinnipeds and birds associated with structure than not? And it was very qualitative. And the short answer to that was no, not necessarily. And the concern was that actually it was not so much that the predators were being attracted to the fish, attracted to the structure, but more that the predators might be attracted to the structure and then increase the predation pressure on any fish that might be attracted to the structure. So the short answer to that was probably not.
Great, thank you. And that kind of leads into the next question, and I'd like to pose this to Sharon and then also to Olivia. I'd like the question is, we'd like your insight on possible mechanisms of harm for fish that are attracted to artificial reefs or FADs, or invertebrates for that matter too. And in thinking about what these mechanisms of harm might be, and Sharon, you've just mentioned one, the questioner wonders if that idea would change if we went to very large arrays of wave or wind devices. So what's your thoughts on mechanism of harm, if there is one? So Sharon, do you want to go ahead, and then maybe Olivia, you could address that too.
Sure, I'll start. Well, so one of the concerns is increased predation pressure, which we just touched on. The other could be that the habitat itself is not conducive for the fish completing its life cycle if it were to, like a reef complex, for example. And so conceivably, the fish, you know, I didn't want to speculate about how we go from a surrogate or a small number of foundations to a commercial installation, but from what I've been able to gather is the larger and more complex the structure, the better it is for fish, especially some of the commercially and recreationally important fish. So the more, you know, again, this is sort of best professional judgment, but it seems that 1 or 2 anchors, 3 anchors, 5 anchors is probably not going to do much. But when you get maybe dozens, you may start to more mimic something that's more complex, like a natural reef complex, and that may actually be better for fish. But I'd love to hear what Olivia has to say. And as far as harm, we couldn't really ascertain any situation of harm. Again, we're not doing the kinds of studies in depth that Olivia is doing, looking at condition and so forth. We are really just looking at the assemblages. The fish do use whatever structure is available, but we could not really come up with a solid mechanism of harm.
Thank you.
Yeah.
Olivia, would you like to talk about that a little?
Yeah, I can say some few things, but I'm not like working on this. But there's one theory that is called an ecological trap. That, for example, fish aggregation devices, they can work as an ecological trap. They just attract the fish without benefiting the fish, and it can come to fitness losses, for example. But yeah, I am not involved in this project, but it's also an interesting question. I think what is the negative effect of these aggregation devices, for example. And also when you install large arrays or parks, you can you install like no fishing zone, and of course you can get increased fishing pressure around the zone, and fishermen and crab fishing waiting for the organisms to get out of the park and to move around. So that's 2 things what I see as problematic.
Yeah. Thank you. Thank you, both of you. We have another question here that really relates more to tidal devices, and I know each of you have just, Sharon, you touched on this about Puget Sound a little bit, and Olivia, I know you're starting to work with turbines. The question is, do you think there is implication to the attraction of fish or other organisms to devices that could increase the risk of strike or collision with a turbine?
I guess I'll go first. This is Sharon. I would say that to me that risk seems minimal. And the reason I say that is because most of the fish are going to be attracted to the foundations, are probably going to be remain around the foundations. And I still think that what we have learned from fish avoidance of turbines and strike, that probably collision risk for fish. I'm generalizing because certain other types of devices, new devices may be different, but blade speeds are slow, et cetera. It appears from what we've learned that strike risk is low. So I would say, based on what I understand about strike and collision risk and fish attraction, that probably the risks are minimal.
Great. Olivia, do you have any insight?
Yeah, of course. I just started to work exactly with this kind of questions and with different devices. And one of this is the power kite. That is a new project. And here you have a kite that is quite fast. So we are a bit concerned what is happening when it goes like 10 meters per second or something and moving around in the water moss. And that's something that needs to be observed, of course. And that's one important thing. We need observations on the strikes and to clarify if it's a risk or if it's just if we don't need to care about it. And I also think it's really species specific in both fish, and then also you have, for example, seals in several areas, or harbor porpoises, and how they behave. So it's really important to continue with observations. And yeah, I'm also curious about this question.
Great, thank you. I have another question that I think probably could go to both of you. How important, and I think Olivia touched on this a little bit, but how important do you think assemblages of biofouling organisms on FADs or artificial reef surfaces are in attracting fish? And further, putting that in the marine renewables context, how much of a difference or how well can we do with anti-fouling measures on the devices themselves to cut down this attraction? So both Sharon and Olivia, if anyone wants to take that.
I'll take a quick swipe at that one. I do think that the literature indicates, and Olivia's study seems to indicate, that the increased complexity of the structure, so that biofouling community does add to that increased complexity, will probably provide more habitat. So that does matter. I think it does. And the other issue that's come up lately is the potential for structure to biofoul, and I think this comes from what we know about harbors and such, about attracting or biofouling of non-native organisms. I'm not going to touch on that, but just was something that I've been running across more of lately. Yeah, so biofouling probably will increase the attraction. And certainly what we know about FADs, like in Hawaii, the more stuff you hang off the structure, netting, anything, stuff that you put on the structure, the more fish seem to be attracted. And I think, again, with reefs, the more complex they are, the more habitat. So, yeah, anti-fouling, do we want to do that? How important it is? Well, I think it's important for tidal or wave device operations probably not to have tons of biofouling. May affect the way that they operate. So I'm sure that biofouling, anti-biofouling paints and coating can be applied. Is there going to be an effect? Yeah, just because of the complexity is probably, as far as I can tell.
Great. Olivia, any thoughts?
Yeah, I totally agree with Sharon, and we've been showing on our wave energy buoys, for example, that we have from a lot of blue mussels growing on the buoys. We haven't any biofouling on them, any biofouling measures. We just had a fouling, and we've been looking at how much it grows. And after a while, you could see like the mussel clumps falling down, and on the seabed they were establishing new habitats for example, hermit crabs and so on. So the whole ecosystem was like developing in and around the wave power park. And yeah, of course, you have to keep it in mind when you like to have some anti-fouling measures, then you reduce. Of course, you reduce the biofouling and you reduce the complexity and the habitat for other organisms, or feeding also the food for other organisms.
Great. And we have one last question here. We hear so many of the risks associated with marine renewable energy devices. At least this is how the industry, I think this is an industry question. We hear about so many risks and very few benefits that might accrue from these devices. Is it your opinion that we can consider increasing habitat and attraction of fish and other organisms to these devices as a benefit of marine renewable energy development?
I guess I'll jump on that first, and I think that I think Olivia touched on this really well, that if they even associate a fish, if we increase the fishing pressure on them, that could really act as a sink for the population. But I think there could be some interaction between, providing fish habitat as a benefit and looking at the fishing risk, recreational and commercial fishing risk, and seeing if there's a way to create, I think people are worried about this de facto marine preserves because of minimizing fishing pressure around these parks, wave energy parks, but then the benefit of providing habitat for fish. So there will be an interaction there. Olivia touched on that really well, but I do see that potentially as it's a benefit for fish and potentially not such a great thing for the fishermen unless they can fish around the park and potentially, like Olivia said, increase fishing pressure around the park. Olivia probably has a better insight on it than I do, but that's not the only thing I can think of.
Olivia,
yeah, it was also like I said before, it can really contribute to higher marine biodiversity in total, not only in fish but also in other species, and thus from ecosystem services. It can really, that it's not like getting even more pressure on the marine environment, but also contribute with habitat and with the reef effect, for example. So this is one of the positive effects. But what else? That was the thoughts I had.
Great. It sounds like both of you are saying this is a potential of a benefit or a positive effect, but that we probably have to look at how we manage and regulate around these for fishing for it to maintain being a positive rather than an additional risk. Is that fair?
I think that's fair.
Great. Okay, I think we've come to the end of our questions. So as we wrap up, if anyone on the line wants to ask an additional question, please do so. Otherwise, I want to thank you very much for attending today's webinar. As with our other webinars, we have recorded this, and it will be available on TESIS at the address you see on your screen. You will find a recording of the presentations and the questions and answers, as well as copies of the slides in a few days. Please watch for announcements of future webinars and other events on TESIS. If you're not already on our mailing list for webinars, please join us. There's for our webinars and also our bi-weekly TESIS blast that will tell you what new both events are going on and also new content on TESIS. And with that, I'd like you, on behalf of our team here, I'd like to thank you, and we'll conclude the webinar. And thank you very much to our speakers, Sharon and Olivia.
Thank you.
Thank you so much for joining today's conference. The session has now concluded, and you may disconnect.